Hello again. Today we're going to talk about acid and base strength, or specifically two ways to find the strongest acid or the strongest base and have a measurement of that. All right, let's take a look. Okay, determining acid and base strength. So let's look at the acid equilibrium constant. So you know about equilibrium, but let's put an equation up here to remind ourselves of what that's about. Let's see, I'm going to just choose that as an example. Acetic acid from vinegar. Okay, the chemical formula for that is H. So the formula starts with an H. That gives you the indication that, yeah, it's an acid. Now that I've written the formula on here, is this a strong acid or a weak acid? Ooh, so you gotta have those 6 strong acids memorized, and this is not one of them. So this is a weak acid. Strong acids are, well, from the periodic table, find chlorine, and right underneath it is bromine and iodide. So we got 3 of them. And then the others, you just have to remember it's perchlorate with that H plus or perchloric acid, nitrate with an H plus, nitric acid, and sulfate. This is a 2 minus, if you remember your polyatomic ions. So there's actually 2 hydrogens, sulfuric acid. Okay, those are the 6 you have to have memorized, and that's not one of them. So you know it must therefore, by default, be a weak acid. If you put it in the water, water will serve as the base. This is the acid, so this must be the base. And it's weak, so we get an equilibrium. We also said in a previous video that weak acids are also weak electrolytes, meaning they don't, all the molecules do not fully turn into ions. Some do, some don't. So a few of these molecules will react with water, act as an acid, meaning, hey, this molecule, acetic acid, time for you to donate an H. That's what an acid is. It's an H plus donor. Bases, you're an H plus acceptor. So water, get ready for an H plus. It's coming from this molecule. H plus is kicked out, leaving behind this piece of the molecule. It's missing the H. And it comes off with a positive charge, leaving the fragment behind negative. Hey, that's acetate ion, one of the other polyatomic ions. Water, you're a base, so accept an H. Oxygen, you have 2 H's. After you accept an H, you have a third. And that hydrogen came over bearing a positive charge, and it's still there. There you go. Okay, so this is the equilibrium reaction. What it means is that sometimes acetate ion grabs an H plus from hydronium and forms these 2 products, right? The reaction goes backwards, so that when these 2 things react, they make the stuff on the left. And that's what the arrows mean. Back and forth it goes. Okay, it's an equilibrium. At some point, you're going to have all 4 of these molecules in solution. And it's found, nature's found this balancing point. And it continues to go back and forth at equal rates. So you have the concentrations of these molecules don't change. That's an equilibrium reaction. And we can write the equilibrium expression from that. The equilibrium expression, or the equilibrium equation, a couple different names for it. That's where you put products over reactants, and specifically their concentrations. And we'll be measuring concentration and molarity. So, and that equals some constant, some equilibrium constant K. All right, so what are the products? Acetate ion. And hydronium ion. All divided by acetic acid. And then water is a liquid. So you remember, no liquids or solids show up in the equilibrium expression. So we just have this molecule here. And that equals the equilibrium constant K. Now, let's talk about strong and weak acids, or acid strength, rather not, yeah. So if you're just trying to compare, hey, we got two weak acids, which one is better at being an acid? Which one is stronger? You could get the equilibrium expression and its equilibrium constant. And from that, you can get a feel for which one's stronger. Now, how's that? Well, remember the equation, the equilibrium expression, places products over reactants. And for any equilibrium reaction, if K is greater than 1, then products are favored. There's more products than reactants. And so K will actually tell you the ratio of products to reactants. What does that mean? Well, if you have more products, then this acid created more H+. It acted as an acid. Hey, if it acts as an acid, it's better at doing it. It's a stronger acid. Yeah. And that's all you do. It's like, well, if you can look up the K values, higher, I should say higher. I shouldn't say higher. I should say larger. Larger K means more products. And that means fewer reactants. The reactants reacted. So your acid reacted, released H+, and it's a stronger acid. So larger K means a stronger acid. Excellent. So sometimes if you're talking about, hey, here's the acid equilibrium or the equilibrium reaction for an acid-base reaction, and we're trying to figure out, hey, how good is this acid? We might be talking about the acid equilibrium constant. So sometimes you'll see a lowercase a right after the K. K means equilibrium constant, and a Ka is the acid equilibrium constant. Nice. Oh, in my notes, I got another example. If you think about a strong acid, like HCl, it can react in water and form hydronium ion and chloride ion, right? And it's a one-way reaction. There's no reactants left over. It's all products. All products. So you could say the products are completely favored in this reaction, right? And so therefore, when products are favored in an acid-base reaction, that means you have a strong acid. The larger the K, the stronger it is. For anybody who likes math out there, if you wanted to write the equilibrium expression, I mean, you're not supposed to since it's not an equilibrium reaction. We don't have a double arrow here, but you can still write it out and see what it looks like. If you'd write products over reactants, you're going to have some big number divided by 0, right? There are no more reactants. They've all reacted, the concentration is 0. And as you divide by 0, or the limit of when the denominator gets smaller and smaller, approaches 0, the limit of that goes to infinity, which is the biggest K of all. So there you go. That's another way to rationalize this by saying, hey, when K is larger than 1, then products are favored, you have a strong acid. And in the extreme case, when K goes to infinity, much larger than 1, you must have a strong acid. So larger K, stronger acid. Cool. All right, what else do we need to know? Oh, one more thing. Back up here, this equilibrium reaction, properly speaking, you need an acid with a base to get an acid-base reaction to happen. But sometimes we're all focused on the acid. So here is another way to write the equilibrium expression, or write the acid equilibrium expression. You could say, start with your weak acid. I'll pick acetic acid again. It's an equilibrium since this is weak, AQ. You could just say, hey, this releases H+, and you get acetate left over. And then from that equation, you could just write the Ka. You're getting H+, the products, right? Put the products divided by reactants, put the products on top. Put brackets around those molecules so you know, oh yeah, we're supposed to put in the molarity, the concentration of each of these things, divided by the concentration of our reactants. And there's the equilibrium expression. If you draw it this way, it's kind of like a net ionic equation in a sense. And let me grab the cut and paste button here. I'm gonna copy that, put it right down here. And then let's compare. They look pretty similar, don't they? Where's my pen, please? Get that back. So we got acetate on the top, got acetate on the top. We got acetic acid on the bottom. The only difference is here there's H+, and here there's hydronium. So H+ equals hydronium. They are equivalent. They mean the same thing. So if someone ever writes the equilibrium expression for you, don't get flustered if you sometimes see H+ or hydronium. They mean the same thing. Cool. Okay. So we got that. And the most important feature is the larger the Ka, the stronger the acid. Nice. That's one way to choose the strongest acid. Look at their Ka values, pick the larger. There you go, that's a stronger acid. Another way is to look at the pH. So how much, what is the pH when this one acid's dumped in water, and what's the pH when a different acid is dumped in water? In that case, it's the lower pH is the stronger acid. Let's look at that in a little more detail. Okay, so let's measure the acidity with pH, or using the pH scale. Okay, let's start out by defining this using water. If you take two water molecules, turns out two water molecules can do an equilibrium reaction. So yeah, if you just have pure water, the purest, purest water you can think of, ultra purified, whatever. There's only water molecules in this system. Nature says, not so fast. I'm going to create a couple more molecules for you. So it turns out that, remember before we defined amphoteric? Amphoteric means a molecule that can act as both an acid and as a base. So let's let this water molecule act as an acid, and this one can act as a base. I know that's weird, but that's actually what nature does. So in pure water, and anywhere, like in the bloodstream, blood is an aqueous solution, in the lake, rivers, tap water, wherever, soup, whatever. Sometimes the water, when they collide, one might be an H+ donor, an acid. So hey, water, give away an H+. This oxygen had 2, and then it only has 1. It actually becomes hydroxide ion. And then the other molecule, the other water molecule, will be the H+ acceptor, the base. So one water molecule releases H+, and the other water molecule binds to it to form hydronium ion. And then what you get are equal quantities of hydroxide ion and hydronium ion. You get equal quantities of an acid and a base. And that happens in pure water. If you write the equilibrium expression for this reaction, which always happens in water, you put the products over the reactant. So the products are hydroxide ion and the hydronium ion. And then you divide it by the reactants, but both reactants are liquids, so you leave them out. There you go. And you could call this the Ka, because there's the acid being created. You can also call it a Kb, meaning, hey, this is the base reaction, base equilibrium reaction, because they're producing hydroxide ion. Yeah, but scientists say, well, this is actually the Kw, water's equilibrium constant. So this happens all the time. And what's really, really weird, I don't quite understand it, but it's nature, she's making the rules. This equilibrium always works, no matter what is dissolved in the water. And it turns out we've been able to measure it. So the equilibrium constant for water at 25 degrees Celsius. So if you keep the temperature at 25 degrees Celsius, this value is truly constant, equilibrium constant. It doesn't change. It's equal to 1.00 times 10 to the minus 14. Put anything in the water, this equilibrium will still be true. Just a fact. Okay. Doesn't matter what's dissolved in there. Always true. Well, and then that's only true at 25 degrees C. No matter what is dissolved in water, no matter the solute. Okay, so let's say we dump in a strong acid in there. So some examples. What if you have a 1 molar HCl solution? Well, what's HCl? One of the strong acids, right? We had to memorize that. Hopefully that caught your eye. HCl, wait. Oh yeah, this completely dissociates. It completely ionizes. If you have, well, what's M stand for? Moles per liter. So if you have 1 mole of HCl molecules per liter of solution, all HCl molecules have split into H pluses and Cl minuses. Or in other words, in this 1 molar solution HCl, there's 1 mole per liter of H plus ions. Cool. We now know the concentration of this. Remember, whether you write hydronium or H plus, they're the same thing. Let's move this out of the way. There we go. So let's look at this equilibrium expression. This is a water solution, so this equilibrium is always true if you have water, and we do. This is aqueous. So the hydroxide ion concentration times the H plus concentration. Now you're right, you can pick H plus or hydronium, your choice, they're the same thing. It's equal to 1.00 times 10 to the minus 14. And we just discovered from the definition of a strong acid, if you start with 1 molar HCl, then you have 1 molar H plus. So this number is 1 molar, and I'll just put in a 1. We'll take care of the units later. And so 1 times hydroxide ion, no, don't do that. It's going to be 10 to the minus 14. Yeah, that's what it is. Sorry, not every day I get confused by multiplying by 1. I'm looking at my notes. I actually didn't have 1 molar. That's what threw me. Okay, but I got it right here, and so we're done with it. So what's the bracket mean? Bracket means molarity. So there's the unit. So this is weird, I know, but if you have a very acidic solution, 1 molar HCl, by the way, that's about the same concentration of HCl as in stomach fluid. Well, it's a pretty strong acid. Turns out, you look in stomach acid, you can detect a tiny amount, 1 times 10 to the minus 14 moles of hydroxide ion per liter. There's still a little bit in there, so that when you multiply the concentration of hydroxide by the concentration H plus, you got to get the equilibrium constant Kw. 1 times 10 to the minus 14. Yeah, there's a little hydroxide in there. Okay, another example. What if you have 0.1 molar NaOH solution? Okay, well, sodium hydroxide is one of the strong bases, right? Or your solubility rules. Salts using sodium should be soluble. This should completely dissolve, and it does. When sodium hydroxide as a molecule goes in water, Na pluses, sodium cations, separate from the hydroxide ions, and they all do it. So in one molecule, there's one hydroxide ion. So if you have 0.1 moles of sodium hydroxide per liter, all 0.1 moles per liter form hydroxide ion and sodium ions. And now we have the concentration of hydroxide ion. So we said hydroxide ion times H plus ion concentration is equal to 1.00 times 10 to the minus 14. If you use this enough, you start to memorize it, but I will give you this equation on exams. So you do not have to memorize it. You just need to be able to use it. Okay, and then for this solution, strong base, we're told how much hydroxide ion there is. It's 0.1. And now let's do the algebra. Divide both sides by 0.1. And you can calculate how many H plus ions are present in this 0.1 molar sodium hydroxide solution. If you do the math, it's 1.00 times 10 to the minus 13 unit. Brackets means molarity. Yeah, minus 10 to minus 13, that's a tiny number. But it's not zero. Pretty close to it, but not zero. So when you multiply this times 0.1, you get the equilibrium constant of water, the Kw. Nature's rules. Okay, why was I doing all this? Well, two reasons. One, there are times when you're giving one of the two things. You're either given the hydroxide concentration or you're given the H plus, and then you're asked for the other one. So you'll be using this equation all the time whenever you're given either one of these, hydroxide or H plus, and you want to find the missing one. This is a great equation, allows you to do it. Second reason, can I get both of these on the screen at the same time? Almost. Okay, lots of H pluses. We get, well, the constant, let's write it out. I didn't. Now, so I just put 1.00 times 10 to the 0 power. Now that's weird, but that's what it is. 1 molar H plus could be written like this, 1.00 times 10 to the 0 power. If we had, let's do a different example, one that's actually in my notes. If you have 0.1 molar of HCl, then you have 0.1 molar of H plus, and in scientific notation, that's 1 times 10 to the minus 1 molar. Okay, and I think I can get that on the screen as the other one. Yeah, there it is. Okay, so we had, let's get this out of the way. Okay, lots of acid, we have a relatively high amount of H plus. Lots of base, we have a very low amount of H plus. So what's the most important feature of this number? It's the exponent. If you look at the exponent first, you can quickly see the difference between these concentrations of H plus. And when H plus is super, super small, negative 13, you know there's not much H plus. So there has to be a lot of OH minus. It has to be a very basic solution. But if H plus is relatively high, like -1 turns out to be, it's much higher than 10 to the minus 13. So this is a higher number than -13. If this is high, then you have a large amount of H plus, and it's an acidic solution. In other words, it's all about the exponent. The exponent is the most important feature. If this is a 2 instead of a 1, then sure, it's twice as concentrated. But changing this number in front doesn't change the overall concentration as much as changing this, right? If you change this to a -2, 1 times 10 to the minus 2 is 10 times less concentrated. So the exponent is the most important feature. So chemists rather, decide to run over to the math department and say, hey, math department, you got a function on the calculator that tells me more about the exponent? They thought about it a minute and said, oh yeah, the logarithm key will do that. Okay, so why do you want the logarithm? Well, I just want to know what the exponent is, the power of 10. Oh, the power of 10. So let's look at the power of H, the pH. The power of H plus. So I want to know the exponent. And then let's not totally ignore this 1 in front, because it does affect how concentrated the solution is. So we're going to find the pH. We're kind of focusing on the exponent of our concentration by using the mathematician's logarithm function. So take the log of the H plus concentration. And if you grab your calculator and just put in 1 times 10 to the minus 1 and hit the log button, log base 10, your answer will be a -1. And if you put in 1.00 times 10 to the minus 13 and hit the log button again, the answer will be -13. And the chemists are like, -1, -13, let's get rid of that minus sign. So after we press the log button, hit the change the sign, the plus minus button, and make it positive just for convenience. And that is the pH scale. So I'll squeeze it in. How about if I change the color? Will that be helpful? So right here, let's do this one, the acid example. For the 0.1 molar HCl, lots of HCl, the pH is equal to negative log of, 0.1, or you could put in the scientific limitation. It's the same thing. You can try it on your calculator. The log of 0.1 will give you a -1. The log of 1.10 to the minus 1 will give you a -1. And then you change the sign. So the pH of 0.1 molar HCl is equal to 1. And then the pH of 0.1 molar NaOH, that took more work. We had to figure out how much H plus ions are there. And then now we measure the pH. It's the negative log of the H plus ion concentration, which is negative log of 1.00 times 10 to the minus 13. Punch that in the calculator, and the pH will be 13. And then you and I will have to get used to the idea that as pH gets bigger, the H plus concentration gets lower. Or a better idea is higher pH means it's more basic, which means more H plus ions. Hydroxide ions, sorry, did I say that wrong? I did. More hydroxide ions. More hydroxide ions because the hydroxide ions are basic. And then lower pH equals more acidic, right? So stomach acid, very acidic. 0.1 molar HCl, that's a lot of hydrochloric acid. The pH is equal to 1. So with a lower pH, that means it's more acidic and more H plus ions. And that's your pH scale. And what happens when they're equal? Well, let's find out. if you have equal amounts like you do in pure water, right? 2 water molecules, 1 molecule of water plus a second molecule of water makes 1 molecule of hydroxide, 1 molecule of hydronium. You have equal quantities. So for this one, you can say, well, hydroxide ion equals hydronium ion concentration, right? That's what it says. One of these plus one of those makes one of these and one of those. It's a 1-to-1 ratio. They're the same if you have pure water. Nothing else dissolved in it. It's going to be a neutral solution because there's nothing in here. So how many hydroxide ions and hydronium ions do you have? Well, right now I don't know. They're the same, but I can substitute into this equation. Hydroxide ion is the same as hydronium. So instead of writing hydroxide, let's substitute hydronium. And then you still have this other one. And it still must equal 1.00 times 10 to the minus 14. So all I did is say, hey, since they're equal, instead of writing hydroxide, I can also write hydronium. And that's just because they're equal. And now this times that is this thing squared. I'm running out of room, so I'll put it over here. This thing squared is equal to 1.00 times 10 to the minus 14. How do you get rid of the square? With the square root. Take the square root of both sides. And now we know how many hydroxide ions there are because it's the same as hydronium ions. And it's the square root of 1 times 10 to the minus 14. Square root of that is 1.00 times 10 to the minus 7. Now what's the pH of that? Well, pH is the negative log of the H plus ions or hydronium ions, which is 1.00 times 10 to the minus 7. Put that in your calculator and you get 7. So pH 7 means neutral solution, and technically it means equal amounts of hydroxide and H plus ions. Not that you don't have any, right? Because water always has some hydroxide and some H pluses, and even if it's pure, this equilibrium is always true. Number of H pluses times the hydroxide ions equals this tiny number. So yeah, we have a tiny amount, 1 times 10 to the minus 7 molarity, moles per liter. Those are tiny amounts, but not 0. Anyways, here's our pH scale. 7 is when they're equal. Below pH 7, it's more H pluses. Above 7 is more hydroxide ions. And that's our pH scale, acids and bases. Nice. Okay. Anything else we need to cover? Well, let's get just a little more comfortable with some of these equations, a few sample problems. Well, I guess there's 3 types. So let's do all types. What is the pH? If hydroxide ion concentrations equal, I don't know, make up a number, 3.2 times 10 to the minus 6 molar. You look at the top of your exam sheet until you find this equation, pH equals negative log of the hydrogen ion concentration. And then do your substitution. Well, the hydrogen ion H plus concentration is 3.2 times 10 to the minus 6. Put this number in your calculator, hit the log button, remember to change the sign, and then you'll get a positive 5.5. The pH is 5.5. Question 2, is this solution acidic, basic, or neutral? This one you have to remember on your own. Remember that pH 7 is neutral, lower pH, and that's what this one is, lower than 7 means it's acidic. Cool. All right, another sample problem might be, hey, what's the H plus concentration? At pH 4.4, no, 4.7. I like the number better. So if you know math, you can undo this equation here, reverse this, but at the top of the exam key, I will have done it for you. Just look for this equation. The hydrogen ion concentration is equal to 10 to the negative pH. Yeah, so what's the pH? 4.7. So the hydrogen ion concentration is equal to 10 to the negative 4.7 power. And you put that in your calculator, find the 10x button. You know, in your calculator, put 4.7. Don't use the subtraction key, use the plus minus key. Make sure it's a negative number, negative 4.7, and then hit this key. At least that's how it works on my calculator. And then rounding off the two significant figures, I got 2.0 times 10 to the minus 5. What's the unit? Well, what does brackets mean? Moles per liter, or big molarity, big M for molarity. That's not too bad. The other variation, last sample problem, would be, hey, what is the hydroxide ion concentration at pH, and then I'll just pick a different number, pH 8.9. Okay, now it's going to take two steps. Which equation has hydroxide ion in it? This one, the ion product constant for water, the equilibrium expression for water. Hydroxide ion times H plus ion concentration is 1.00 times 10 to the minus 14. I will give you that equation. So we can find hydroxide ion. That's what the problem asks us to do. But first we need the H plus ion concentration. Well, then let's use this equation first. The H plus ion concentration is 10 to the minus pH. And so pH is 8.9. So 10 to the minus 8.9, put that in your calculator. And don't round it off yet, because we still have to do more math. So I'm going to keep a whole bunch of digits so I can avoid a rounding error. And brackets means M. So there you go. The H plus ion concentration is 1.3 times 10 to the minus 9 at pH 8.9. But that's not what it wants. The question wants hydroxide ion concentration. So now let's use this equation, which says hydroxide ion concentration times H plus. Well, now I know what the H plus concentration is. It's this number. These two numbers must always equal 1.00 times 10 to the minus 14. Come on, there it goes. And then to do the algebra, we have to divide both sides by 1.2589 times 10 to the minus 9. Divide this by 1.2589 times 10 to the minus 9. And then hydroxide ion concentration. If you put these numbers in your calculator correctly, that could be challenging if you're not used to putting scientific notation in your calculator. You could get your calculator to give you bad answers. So yeah, be careful and find out how to do that. Here, let me give you the answer first. So if you put this in your calculator correctly, you should get to two significant figures, 7.9 times 10 to the minus 6 molar, right? Brackets means molarity. Your calculator, if you need to get 1.00 times 10 to the minus 14 in the calculator, you're probably going to have to type in 1. So hit the 1 key, the decimal key. I know, step by step. I apologize for those of you who know how to use your calculator, but some students don't. And then this is going to be really troublesome for them. On some calculators, there's an EE button. Other calculators, there's an EXP button. Hit that button next. And EE or exponent means 10 to the, and then hit the plus minus button, then hit the 1 button and the 4 button. So you type in EE negative 14. So that'll tell your calculator, hey, we're doing scientific notation. And then hit the divided key, the division key, and then type this number in the same way, 1.2589. And instead of typing X10, hit the EE button and a -9. That should give you the correct answer. Another way, a longer way, is to type in the 1, the point, the 0, the 0, and then the times key, then 10, and then the little caret symbol, the exponent, to the plus minus 14. And I forgot, we should have started the whole thing with the parentheses. Okay, so you can tell the calculator, hey, this is all one calculation, and divide it by the other one. So that's the division key. Put in the other number with the parentheses. If you leave out the parentheses and you're doing the 10 to the little caret, little exponent, the calculator is going to do some funny math and not give you the correct answer. So bottom line is, you can use parentheses, for every scientific notation number you insert in the calculator, cap it, group it with parentheses, or the easier method is to use the EE button or the EXP button. Okay, there is a worksheet on Canvas to help you practice using your calculator, because I know it's a big deal. You want to get the right answer. So take a look at that. Take care. I will see you in the next video.